Good morning, good afternoon, good evening, depending where you are. Welcome to our sixth edition of the IEEE Geoscience Remote Sensing Young Professionals and International Society of Photogrammetry and Remote Sensing Student Consortium Summer School 2020. And I have the pleasure actually to start these presentations. Before that, just a very short video of the ISPRS student consortiums led by Cheryl Rose Rice.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the sixth edition of the IEEE-GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
This was a wonderful explanation about the ISPRS student consortiums and their activities. Now, another video from Paulo Gamba, that is the president of the Geoscience Remote Sensing Society this year.
Good morning, my name is Paulo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere and space, as well as the processing, interpretation and dissemination of this information. So what are the activities of the IEEE Geoscience Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, dataset by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the young professional event, by means of student grants, by means of the Thai forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and dataset. We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each other's and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Wonderful talk from Paulo Gamba. I just saw in the chat that we have different participants from Brazil, Pakistan, from Peru, Indonesia, Colombia, Luxembourg, Serbia, Ethiopia, Bangladesh. Yeah, please just write down your name and country and be welcome actually to this lecture. I will just invite now Clodovil. He is from the Federal University of Minas Gerais. He will be conducting then this talk and will be also presenting the sharing team as well as our industry distinguished lecturer, Rohit Singh. Well, Clodovil, your microphone is just, yeah. So
Okay.
welcome actually, and again, thank you actually very much for accepting actually this task and also helping to support our event. So the room is yours now. I will be here in the background for technical issues. Again, thank you very much. Please introduce our sharing team and our distinguished lecturer. Thank you again.
Okay, Veraldo, thank you very much. I'd really like to thank the organizers for inviting me, for having the honor of chairing this session here. The event itself is going very well. It's an excellent event on the 2020 IEEE-GRSS and ISPRS Young Professionals and Student Consortium Summer School. In my role as chair, let me again introduce you to the participants of the board here to follow the presentation. I'll be acting as the chair, of course, and we have Professor Aloir Porfírio Dalpós from UNESCO as the invited researcher, and as a student and young professional invited person here is Nájila Souza da Rocha from the Federal University of Rio Grande do Sul. We'll be following you up in your questions and your discussions following the presentation, which is going to be made by Rohit Singh, who is the managing director of Esri's Artificial Intelligence Research and Development Center in New Delhi, India. Rohit leads the development of data science, deep learning, and geospatial AI solutions in the ArcGIS platform, which everybody, of course, knows. Rohit is very passionate about deep learning and its intersection with geospatial data and satellite imagery. And he's a graduate from the Indian Institute of Technology in Kharagpur. Has worked with computer vision startups and with IBM before joining Esri. So in Esri, he conceptualized, designed, and developed ArcGIS Python API, ArcObjects Java, ArcGIS Engine Java API, and ArcGIS Enterprise for Linux, which are all products and initiatives that we praise very deeply because of their impact in our community. So without further ado, I once again thank Rohit for being here with us, and welcome him to the talk, and give him the floor. We'll be in the background following up the questions you might have on the chat channels on YouTube and elsewhere. Okay, so let's begin. Rohit, thank you very much again for being with us, and we're sure to have sure lucky to have you with us here. Let's make the lemonade from this lemon of a pandemic, which will allow us to have such distinguished guests and distinguished participants from all around the world, as Geraldo has said. Thank you very much, Rohit. You're on.
Thank you, Claudio. So it's an incredible opportunity to be here, and with having people from around the world, it's awesome that so many people from so many different countries, so many different time zones are here, and I'm so excited to tell you all about what's new in applying machine learning and deep learning to geospatial data. So I'm from the New Delhi R&D Center of Esri. That's where we develop a lot of these AI capabilities. And so let's get started. So when we talk about geospatial AI in ArcGIS, and I'll be talking with AI with respect to how it's implemented in ArcGIS because of my industry affiliation, but you can get the context of how AI can be used by real users to solve real problems. So when we talk about geospatial AI in the ArcGIS platform, it really spans the entire spectrum. But at its core, it starts with ArcGIS.learn, which is a Python module in ArcGIS API for Python. So this module lets you easily train a wide variety. Right now, we've got 29 different deep learning and machine learning models, and you can train them using a simple, consistent API across all of those models. So, of course, you can train models using your own frameworks. You could use TensorFlow, PyTorch, you could use GitHub repositories, but it's hard. You need to do the plumbing work, connecting it to a GIS system, getting the data and getting the results out. And we've kind of made it all seamless. And we've created a very simple, consistent API that you'll see here, with which you can train a variety of models. And that is to make AI more approachable to end users. So ArcGIS Learn has support for deep learning and machine learning across a number of data set types. And a big one is imagery, of course. Deep learning can be applied in so many ways to imagery, but it can also work incredibly well with other types of data, such as 3D point cloud. We've applied it to tabular and feature data, to time series. Sometimes you've got scanned maps and you want to apply computer vision techniques, and we've got support for that. And a new area is for getting information out of unstructured text using natural language processing. So let's start with deep learning with imagery. And there are a number of tasks that you can do when applying deep learning and computer vision to imagery. And perhaps the simplest one is identifying what's in an image. So in the case of GIS and remote sensing, we are talking about geographical objects or features, and we want to classify them as belonging to one of multiple types. There could also be multi-label classification. So there could be a house. In this case, it's single label in this example, where we are classifying a house as damaged or undamaged based on how it looks like in the remotely sensed image. But it could be, does the house have a swimming pool? Does the house have a solar panel? And maybe one house has both of them. So it could also be multi-label classification. So we've got a model, we call it feature classifier, but really it's a thin wrapper on top of torch visions, computer vision models. So any kind of image classifier. So you would have heard of VGG. That's very popular, but slightly dated now. And now there's Inception, there's ResNet, and different variants of these. And you could take any of these backbones, fit it inside a feature classifier, and easily train one of these models. So I want to use this opportunity to also introduce you to where you can find a lot of resources to learn about what I'm talking about. So this is ArcGIS API for Python. That's at developers.arcgis.com. And that comes with a number of guides and sample notebooks. So over here in the guide section, there's a whole section on applying deep learning with ArcGIS. Another resource that we have is the Medium blog post. It's GeoAI publication on Medium, where we blog about a lot of these applications of AI to GIS and remote sensing. We actually wrote a blog post about this specific use case of how USAA, which is an insurance provider, was able to take deep learning and the feature classifier and automate the task of identifying which houses are damaged after a fire, so claims can be processed in a quicker way. So this talks about how we start with some label data, give the machine several examples of houses that are damaged or undamaged, and using the feature classifier, how we can, in a few lines of code, we can train a model, get the results, and also create a model package which can be used for inferencing or deploying it on large volumes of imagery. Another, you typically don't think of taking pictures on a mobile phone as geospatial in nature, but an interesting use case is how we can use it for field data collection. So let me play a quick video to show this. So here you can see how a mobile phone is being used to do field data collection. So it's typically, the scenario is you go out in the field, and in this case, we are doing a tree inventory. So going to each tree or plant and then saying where it is and what plant species it is. But someone who's doing a survey in the field isn't a trained botanist who would know all of these plant species by name. So for that, we can train another feature classifier on these images of plants and flowers, the leaves of those plants. And we are using an open data set called PlantClef, which has over 260,000 images for 10,000 species of plants. And here again, using feature classifier, and this time specifying the backend to be TensorFlow, using the same methodology that I spoke about earlier, how we can train a model that can recognize the species just by pictures of plants and leaves. We can take that model and save it as a compact model that can be deployed on mobile phones using TensorFlow Lite. And our field data collection app, Survey123, now in beta allows you to deploy these models on the phone. So when a surveyor goes out to do a plant survey, tree inventory, instead of picking what species it is, you just point the camera at the plant, and the model is able to deduce the plant species by itself. Of course, allowing the surveyor to override it if it's wrong. But you can see how GeoAI can be taken to the edge to solve a very common problem in field data collection. Now, once you've collected this data, this can be pushed back to the WebGIS, and you can get these kind of applications which can tell you where the trees are, what species there are, and so on. So this example was using the feature classifier, and the whole notebook, if you are a data scientist, you're perhaps already familiar with Jupyter notebooks, which is a browser-based IDE of sorts that look like this, where you can type in your code and you can see the results interactively. We've created a sample notebook for plant species identification. That's the example that I showed you, and it's actually something that you can browse online on the developer's website for ArcGIS API for Python. You can take this notebook, you can download it, and you can actually go through the entire workflow. You can learn about how it works. You can tweak some parameters, and you can play with this, see how it can actually be deployed. So the whole workflow is what these sample notebooks talk about. So moving on, the next common type task is, instead of identifying or classifying the whole image, we want to classify each pixel as belonging to a particular class or a category. So a use case is finding pixels that belong to buildings, or pixels that belong to roads, or doing land cover classification. That's exactly what land cover classification is, that for each cell, what's the land cover class? And that's where we've got a few models. There's the popular UNet model, and that's kind of something you always start with whenever you want to do pixel classification, which is known as semantic segmentation in the deep learning world. Then we've got PSPNet, there's Deep Lab version 3. And very recently, we've added point rend architecture. That's a new architecture that can improve these segmentation or pixel classification models to give very precise boundaries. So it's very useful in finding the exact building footprint to a great degree of accuracy. So typically, deep learning requires a large volume of data, but we've added enhancements to these models, so you can actually train them with sparse volumes of data. So just like with machine learning, how we typically only label a few areas, and that's a traditional workflow. We give examples that this is a forest. The buildings are in the other polygons, and the grassland is in these polygons. So you can give this kind of data to the model, and we've made enhancements. So just by specifying that, you should, when creating the model, when you construct the UNet classifier, where's the code for that? Let me quickly search for that. But yes, when you're creating the model, you can say just ignore the background and train on whatever real data is present in this. The background is in the 0 label here, and we've only provided labels for the other models. And another thing I want to highlight is that we've made it a little easier. So you don't have to start from scratch and create those image chips that are needed to train these models, all using code. We've added tools to ArcGIS that lets you export that training data in the form of image chips. These models need a lot of computation that cannot fit on a small GPU, which has limited memory. So we typically create small image chips that look like this, and these image chips are overlaid with the class label. So you can see what the class label is. And they've come in the notebook. You can then create the model, find a good learning rate, and fit the model for several iterations over that training data. And you can see the accuracy of the models, and you can visualize the results. So you can see how only this much was labeled, but the model has been able to do the pixel classification across the whole image. So model has learned that the purple color belongs to roads, for example, and the blue color is forested areas. So you can take this model, save it as a deep learning package, again, use it for inferencing using tools in ArcGIS. The next task is object detection, a very common task where you want to find what's in an image and what is its approximate location in terms of a bounding box. So just draw a box around wherever you find trees, for example. And here is an example for shipwrecks. So we've got a number of models listed here. SSD, RetinaNet, YOLO is quite popular. You only look once. And not only do they work with satellite and aerial imagery, they also work with what we call oriented imageries, that is, images taken on the ground or at an angle. So this is an example that we were able to find cracks on the road by taking a video feed and using a road cracks detection model. Now, another kind of object detection is known as instance segmentation in the deep learning world. And here, not only are we finding the boxes around the object, but the precise polygonal boundary, like all the pixels that belong to each instance of that type of object. In this examples, we are trying to find building footprints. So let me show you an example of that. We've got a couple of examples, the Woolsey fires example that I had shown you earlier, where we were using the building footprints and just classifying whether that house is damaged or not. Actually, you could use those existing building footprints to train a new model that, given just the imagery, find the building footprints. And this notebook goes through that workflow of how we used a pixel classification model, UNet, again, to go and identify which pixels belong to buildings, such as in these examples here. So that is pixel classification, but it doesn't work when the buildings are right next to each other. You want to call out one building from the other. And that's where you want to use a mask RCNN model. So here's an example of that, where in dense urban areas such as Berlin, in this example here, you've got buildings right next to each other, and a lot of developing countries as well. So that's where you can use a mask RCNN model to get the precise polygonal boundary of each building, and also take out one instance from the next, so doing instance segmentation. So that's where the same typical code that you've seen and are perhaps bored of by now, hopefully. That's the idea. You learn the technique once, and then you can apply it on any model. So create the model, find a good learning rate, and use that to train your model. Now, if you don't pass in a learning rate, we'll automatically find that. So that's using some techniques based on a paper by Leslie Smith, implemented in FastAI deep learning library. On top of it, ArcGIS Learn is built. Actually, it's built on top of several leading libraries like PyTorch, like Hugging Face transformers, FastAI, Spacey. So we've done that hard work of finding what's best to build upon, and created the seamless interface that you can train a wide variety of models using the same API in ArcGIS Learn. So as you can see, here are the results. On the left is the ground truth, and on the right, you can see how the model is able to easily segment out these different buildings using this kind of a mask RCNN model. So all of those models that I showed you, they can actually now be used end-to-end or trained end-to-end in ArcGIS Pro using tools. You don't actually need to go to the notebook and train them. I showed it in notebook because today's audience is technical. They like to have more knobs to tweak, and the notebook and the API lets you do that. But if you are a GIS analyst, you can train all of these models, the ones that I showed earlier, through just tools in ArcGIS Pro. Now we've also added some new models. These can only be trained using notebooks currently. So we got a couple of models to just identify the edges. So this could be used for finding agricultural or residential parcel boundaries. And here's an example here. We've got bidirectional cascade network edge detector and a holistically nested edge detector. So this is just showing some results from that edge detection model. And I'll quickly just show you the edge detection model sample for parcel delineation. So this is using data from Cadista, which is one of our partners. And you can see how even with very limited training data, this is just the number of parcels someone hand digitized on top of the imagery. And we use that to go through the workflow to train this model. So once we have this input imagery and those polygons, we can export that data, get these image chips where the parcel boundaries are overlaid on top of the imagery. And this time we are using a BDCN network to train the model. And once again, the same methodology, and you can see the results. Now you can see how the results are a little noisy, and the post-processing tools, the thin tools in GIS, in ArcGIS in this example, can be used to clean up the results further and get very precise boundaries for these, as you can see in my slides here. So these are the results after post-processing. We've also added a model based on StanNet, which is used for change detection. So, if you take imagery at any 2 times, there's going to be change in every pixel because of changes in lighting and weather conditions. But we are not looking for that kind of change. The change that we are interested in knowing about is the persistent change. So things like where have new buildings come up, or where have new roads come up. And that's the kind of change this change detector model lets you do. So let's take a quick look at that. And here we've got training data. And this training data, in the case of change detection, it needs 3 inputs: the old imagery, the new imagery, and a raster showing where the change has occurred. So here we are visualizing that training data. So this is the before image, this is the after image, and this is a mask showing where changes have occurred. So using this kind of data, we can train a change detector model. We could use different model backbones. In this case, we are using ResNet as our feature extractor and training that model. And you can see how, as we start training the model, we've only done it for 5 epochs here. The model is not working so well. It's not found this change yet. So it's still, we can see it started to learn a little bit. This is the ground truth, and this is what the model is predicting. It needs a little more training, and the notebook lets you iteratively do that. So once I've trained it for 5 epochs, I can train it for 5 more epochs. I can see how whether the loss or the error rate is going down, how the accuracy, the precision, recall, and F1 score is going up, and I can visualize the results. So with a little more training, we can see how the model has started doing a very good job at identifying where new buildings have come up. And that's using the change detector model. So given an input image and an out, a before image and an after image, here we can say that the model is able to visualize where there is persistent change. So in this top right corner, you can see new buildings have come up. That's using the change detector. Now, we've also added generative deep learning to ArcGIS. So you might have heard of GANs, which are generative adversarial networks. And they can be used for, in this case, to translate images from one domain to another. So what does it mean? Well, you might have SAR data and which can penetrate through clouds, and you want to go from that to the satellite imagery, the RGB or the optical imagery. So you're doing a domain shift, and GAN models can do that. So we've added support for pix-to-pix and cycle GAN to do that. We've also added a super resolution model that can let you go from lower resolution imagery, like on the top here, to a sharper, higher resolution imagery. And in the example that you just saw here, we are going straight from the satellite imagery to the rendered map, which has those streets and houses and pools already labeled. So you might be wondering, like, what's the GIS or remote sensing application of those? And a very interesting one is on going from digital surface model to RGB. So in the top half of this image, you can see how it's a DSM, and the bottom half is showing that's the RGB imagery converted from that. So let's see, that's using pix-to-pix, I believe. And there's also cycle GAN. SAR to RGB is using cycle GAN. So let's take a look at SAR to RGB. And in this example, we want to go from SAR data to the optical imagery. And cycle GAN is a model that works with two sets of images. So you've got images of domain 1, which you put in one folder. And for the second domain that we are calling it as domain B, you put them in another folder. And it figures out how to go from domain A to domain B and from B back to A using a cycle consistency loss. So you can see a batch of the training data here once we've prepared it. And you can see cycle GAN actually uses unpaired images. It doesn't even need the images to be of the same area. So given a pair of images, it learns how to go from domain A to B and B back to A. So on the left, you can see the SAR imagery. On the right, you can see the optical imagery. And once again, the same training methodology, more number of losses that this model minimizes, or the errors that it minimizes, you get to see them. And here are the results. So going from this SAR imagery to this optical imagery, or going from this optical imagery to how it would look like if it was captured through a SAR sensor. So the practical application of this model would be that, let's say you've got a cloudy day, you're not able to capture the imagery, but SAR can penetrate those clouds using these radio waves. And using a model that has been pre-trained like this, you can go from SAR to optical. Now, image captioning is another kind of translation of images, but instead of going from images to other images, you're going from images to a textual description of what's in that image. And here are some results from the image captioner model. It's able to identify that in the leftmost image, it says that many storage tanks are near a road. or in the one on the right, the model is able to identify that this is a railway station and there are buildings on the sides of it, and it's able to come up with a caption such as many buildings are on two sides of a railway station. So it's incredible that what these models can learn. And in this case, it's using a combination of computer vision and natural language processing and advances in those. We also have a very good state-of-the-art model for extracting roads. This is using multitask learning. So unlike UNet classifier or the pixel classification models that only identify whether a pixel belongs to a particular class or category or not, multitask learning tries to do multiple things. And as opposed to a human, where you might think that, okay, if I'm trying to learn two things, it'll be hard for me to learn them. What happens is that it's hard, but once the model has figured out both things, uh, one task helps the other task. So in this case, the multitask road extractor tries to identify two things: whether this pixel belongs to a road or not, and if it is belonging to a road, which orientation is the road in? So it's trying to learn the orientation as well, which is a surrogate task. We really don't care about the orientation later, but we train the model on these two things. And in doing that, it becomes a better model and starts giving incredible results. So let's look at some of the results from that model. And here we are using the SpaceNet challenge data for Paris in this example. And using the tools in ArcGIS to export this data. Again, the same methodology, visualizing a batch of data. So the road is overlaid on the imagery. Creating the model. This model works with an hourglass backend and a LinkNet backend. Hourglass is the default and works better in our experiments. And here you can see the result, the model being fit on that data. The API supports early stopping. So if the model is not improving, it'll bail out and say, okay, model didn't improve in like 5 epochs. This is the best I can do. And as you can see, here are the results. On the right is the predictions. On the left is the ground truth. The model is doing a near perfect job of matching the results. So you can save out the model as a deep learning package, and you can inference it in ArcGIS Pro. So I believe I have a project. Yes, here's the project, ArcGIS Pro project, where I've already applied that model over Boston, and you can see how it's doing an incredible job at finding all these roads here. And using a little bit of post-processing, raster to vector conversion, we can arrive at a road network. So there are tools in ArcGIS that let you do this conversion, let you extend these lines by a little bit if they're missing, and you can get very accurate results. Another interesting use case is when you've got scanned maps. So you might have scanned books that look like this, and very often, interns and graduate students are asked to do the painstaking task of let this load up. Taking books like these and digitizing what's in a map, and it's a very tedious, painstaking process. In this case, these are range maps which tell where a particular species of rodents is found. And using the scanned map digitizer, this is a computer vision model. It's using classical computer vision, not deep learning. And using that, you can go and automatically not just extract and digitize the map, but find where it belongs in the whole world map. So even geo-referencing it. And you can arrive at results. Let's look at that. So here's the scan map digitizer, and it walks you through that process of how you can go about it. And there are APIs to go through each of these steps. So and you can visualize the results, intermediate results within the notebook. So going from an input folder where a lot of these images are, you first want to extract the region belonging to the range map. You want to extract the template image showing uh, which this helps in finding where in the world map this map belongs to. And the whole workflow is here. You can tweak these knobs. So when creating the template image, you tell that look at this color, and you use a delta of this much. So the color could be off by so many units, and use some morphological operators like thinning uh, or uh, dilation, and you can get clean results for these steps. And once you've gone through that process, you get web scenes. Let's look at the results here. Animals of the world. Yes. So here are the results visualized on a web scene. So you can see how from this scan map, it's able to come up with such a nice automatically extracted and digitized boundary, the range map. So this is coming from here. So now once you've done that, gone through that process, you can do further analysis, like where is there species, where's the highest density of these species, for example. So another result here, and you can see how closely the results match what you're seeing in the scanned map here. So that was imagery, but we've done a lot more work in other areas of GIS. And one example is with point cloud data. So we've got a model to classify points belonging to a particular class. So point cloud classification using point CNN. So you can use it to find which points belong to power lines in this example, or these posts, and which points belong to buildings. So that also uses a similar strategy. I'll show you some examples of point cloud a little later. Let's keep moving. This is showing an example of automatically finding points belonging to buildings, to vegetation, and to ground. And once you've done that, you can do a complete workflow by taking deep learning, combining it with post-processing tools in ArcGIS and City Engine, and coming up with 3D building models with texture like this. And there's resources on that as well. Let me quickly show that to you where you can find it. Yep. So this is a demo that comes from a user conference plenary, and the notebook is here, and the workflow to go from a raw point cloud to a 3D model for that urban scene is documented here. And you'll find how the model is trained, the results from that model, how you can extract trees, buildings, and end up with this final step. Now, you might be thinking, okay, imagery and 3D. Well, what's incredible is deep learning also works very well with the other kind of data in GIS, which is feature data, tabular, and time series data. So here's an example. We've got three kinds of models. There's fully connected network, which is basically a fully connected deep neural network with you specify the number of layers and how many neurons in each layer, give it that input data and come up with an output. And the output could be, as shown in this example, is to predict the efficiency of a solar power plant based on weather factors. This model also takes inputs from raster layers, so trying to predict where dengue outbreaks may occur given a lot of factors such as bioclimatic factors, the distance from rivers and water bodies, and so on. Now, we also have an ML model that acts as a bridge between ArcGIS and scikit-learn, which has a number of clustering, classification, and regression models. So you could use the same methodology to train one of those models. And we've also recently added a time series model that can let you do weather prediction, for example, or predicting pollution levels. So let's look at a couple examples of that. I'll just quickly highlight, this is a solar power plant scenario where we've got a few solar power plants and we've got some input data about the wind speed, the precipitation, the length of the day, and so on, the temperatures. And we are able to come up with the efficiency of that plant as a label of the solar power plant. And we are plotting the input variables, and you can see there's a cyclic variation in those. And let's go to the part where it's constructing the model. So you can see how we can create a fully connected deep neural network using this, use the same training methodology, and the results, you can see how they are getting a very good R square on doing that prediction. And the same methodology, you could use it using scikit-learn's models. So here we are creating a machine learning model, and you can pass in any one of scikit-learn's regressors. We've chosen the gradient boosting regressor in this example, and the same training methodology, and you again get good results here. And it's similar for time series. So I won't go in the details here, but you can see we are predicting retail sales using deep learning and a time series model. And this is just visualizing different chunks of that time series that the model is trained on. And this model actually works with both fully connected network and surprisingly with convolutional neural networks. So there are networks like inception time and one based on ResNet, ResCNN, I believe. And these convolutional neural networks are giving great results for time series prediction, and that's what we've integrated in this example here. So we just saw these examples. Now, another new area which is coming up a lot is natural language processing. It's now at a level which is approximating human accuracy. And it has many applications in GIS and remote sensing. So going from unstructured text like reports like these and extracting information. So these are fire incident reports and being able to identify where did what kind of incident occurred, the incident type is a collision, number of fire engines was 1, where it occurred was this address, how long the engine was here. So you can label and provide this kind of training data to the model. And once it's trained, this is using an entity recognizer model. You can run it on a number of these reports and come up with GIS layers shown in this example here, where we've extracted these attributes. And we've added a whole new submodule called ArcGIS.learn.text to do that. We also let you do text classification. So basically, in this example, taking some text, in this case, an incomplete address that does not have the country, and classifying it or categorizing it that based on this address, I think it's this country. That's what the model is doing, and how you can see how it's so incredible to do this. And with great accuracy, the model is able to do this prediction. Then there's sequence to sequence. So going from one sequence of tokens, which could be words, to another of similar or shorter length, or a different length. It could be used for translation or summarization. In this example, we are using it to correct the spelling mistakes in street addresses, and also to regularize them into a standardized format. And you can see some results here. Now, all of the examples that I'm showing you, the notebooks for these are available on the developer website. In fact, there's a GitHub repository. Let me quickly show that to you. And this is hot off the oven. We actually released the 1.8.3 version of the Python API 1 day ago. So literally, you are the first to see all of these coming together. And it's so new that we are actually working on putting all of these examples on our developer website. But before they end up there, they end up in this public GitHub repository. And you can already see, how CycleGAN works, the guide for Pixapix, and the road extractor. All of those notebooks that I'm showing you, you can actually take them off of our GitHub, try it out right away. That's the SAR to RGB conversion. So that was sequence to sequence. We also have a number of inference-only models. So going from a story map or a blog from one language to another. And here's an example of that. We got a number of these, like a zero-shot classifier, for example, could be used to say, what's the sentiment of a tweet? For vaccines are coming up. Do people, do they have a positive sentiment about vaccines, or is it a negative sentiment? And how does it change by the area around a country or the world? Now, we could use a zero-shot classifier to do something like that. So this is showing an example of going from German to English using the text translator. So, you might be wondering, okay, all of these are actually, some of them are available on GitHub, these models. I could go to GitHub, I could use PyTorch or TensorFlow. Why ArcGIS Learn? One is that it's integrated with ArcGIS. So going from ArcGIS, getting the data into the model, and getting the results back into ArcGIS is seamless. There's a simple API that I'm sure I've bored you enough, but that's the idea, that once you learned how to train one model, you can go to another model and train it. And there's a huge collection of these geospatial deep learning models. There's also support for visualizing how the model is training using TensorBoard. You can easily install deep learning dependencies. So we've got a deep learning libraries installer. So all the dependencies of ArcGIS Learn, you can easily install that if you're using ArcGIS Pro, or if you're using Anaconda, you can use this new meta package that we have. So to recap, that was ArcGIS Learn, which is a submodule in ArcGIS API for Python, which has many other capabilities for geospatial data science, like raster analysis or big data analysis, something we call as geoanalytics. And we recently added automation for creating dashboards. So, once you've done your analysis, you want to present it to your end users, you can automate and create these web applications just from Python. But not everyone is a trained data scientist and or knows Python. So for those users, we are creating ready-to-use AI models. We now have 3 models on Living Atlas of the world. So there's you can go to Living Atlas, you can search for deep learning, you'll find a building footprint model, you find a tree point classification or land cover model. And these models can just be used right off the bat across a large number of geographies. Now, we trained this model on data from the US, and it works very well there. But surprisingly, it also works in some cases in geographies around the world. So this is an example from Sweden where it's working. And here's Palm Island in Dubai. So let the imagery load up. And you can see, you could take this model, just use ArcGIS Pro. There's a blog post that describes how to use these models in ArcGIS Pro. This is what its title is, and you can read about these ready-to-use AI models. So we just looked at the building footprints model. We also have the land cover classification model, and there's a tree point classification model. And like I showed you, there are tools in ArcGIS that let you easily do that. You don't need to know Python. Analysts can use these capabilities. And these deep learning tools have been enhanced to work with multispectral imagery and more number of models recently. This is another tool to detect windows or objects in 3D scenes that's coming in the new release of ArcGIS Pro 2.7. And finally, to round it off, we've got solutions such as the 3D base map solution, which are used to solve user problems. So what they let you do is go from, create these, going from point cloud or LiDAR to these 3D buildings. And we've got, let's look at some results from that. We've integrated the tree point classification model with this solution. So you can go from a raw point cloud like this, automatically using the solution, you can find which points belong to buildings, trees, and ground. And using the integrated tools in that solution, we can find and cluster those points and say that these belong to these trees. And based on their height of the trees and the spread, we can identify the closest actual tree based on statistical data and replace it with a tree model. So you can arrive at these incredible models, 3D scenes, where it matches the point cloud in a great deal of depth or detail. So that was the tree point classification model used in creating these 3D base maps. So I'm just going to wrap up quickly, another 2 minutes, I think. I believe I went a little over time. Apologies for that. But to sum it up, as you would have seen, geospatial AI is spread across the ArcGIS platform, whether you are a Python programmer or a data scientist who wants to start with ArcGIS Learn or the Python API, or you are a GIS analyst who's using our tools in ArcGIS Pro or Enterprise, or you're an end user who wants to solve his problems and doesn't care about whether deep learning or AI is under the hood. You only care about your results and getting better results. So to sum it up, some key takeaways: there are a lot of models, a lot of tasks. You can use a number of client apps to use deep learning, like notebooks, like ArcGIS Pro, like solutions. It can be scaled using distributed raster processing and ArcGIS Enterprise. Several options for developers and data scientists, and many tools for downstream analysis. Some resources for you to look at. I showed you many of these resources during the talk. So that's if you were to take a screenshot or a picture, this is the time when you can go and take that. We've got samples, guides, and API reference on the developer's website. And many of the new notebooks that I showed you today are on this GitHub repository, the public repository for ArcGIS API for Python, which contains the samples and the guides. And you can actually look at the live pull requests with many of the new things that are being added, that just got added to the Python API. And then there's the Medium blog on GeoAI, which has a number of use cases of how you can take deep learning and apply it to GIS and remote sensing. If you're new to deep learning and you want to learn more, if you want to learn how to apply it in ArcGIS, that's the link. And if you want to learn about deep learning in general or with ArcGIS, you can search YouTube for ArcGIS deep learning. If you want to get under the hood, I would highly recommend Fast AI courses by Jeremy Howard. They're incredible and really a great way to ramp up on deep learning if you know a little bit of Python. So with that, I'll come to an end and I'll be available to answer any questions. So Veraldo, you could, or Claude, you could take over and I'll be here to answer any questions. Thank you so much.
Okay, Rohit. Thank you very much for this great presentation, this great talk. I'll conduct the questions and answers session with the help of Alwir and Najla. Just like to, as an additional acknowledgement of the importance of your talk here, I would just like to point out for the audience that 30 years ago, I was myself a young professional in this field, and the rage of the moment was stereo plotting everything from photogrammetric images to produce large vector databases for urban applications. That has been decisive in our use of GIS in the beginning of that era, when GIS is at its infancy. And right here where I work in Belo Horizonte, we had a very large database of vectors for urban mapping that used to awe many people into, wow, what's that? Everything in the city is part of the map now, it's a digital map. So a mere 30 years later, we're not only doing that, but we're doing that automatically with artificial intelligence and providing such great results as you showed us today. So that's to incentivize our young professionals in the audience to take the most of this talk, to notice that as the direction things are going right now. So you should be aware of that for the next years of your careers. So with that, I'll leave that to Anouia and Najla to conduct questions and answers. And I'll be here with lots of questions of my own. So let's get the audience the precedence in that. Okay, so thanks a lot, Rohit, for the presentation.
Sure. Thank you, Veraldo. And Claude, sorry.
Okay.
Sorry, I
Your
cannot
audio is
hear you.
off.
I moved. Sorry.
Now we can hear you.
Thank you very much for your presentation. It was awesome. I have actually one question. It's more, it's not about your presentation, but it's about deep learning. I have a question. I don't know the difference. I don't know if it has a difference between deep learning and machine learning. Can you answer?
Yes, that's a very good question and a very common question. And I think I should have addressed it. I'm glad you brought it up. So, well, machine learning by definition is learning from data. So you've got some data and the machine learns from it and can apply it. Deep learning is also learning from data. So deep learning is a kind of machine learning if you go by that definition. But I would say that I treat deep learning as slightly different from traditional machine learning. And I think that's where your question is coming from, like what's so different about deep learning? And to me, it's different because one is that with deep learning, you are now getting results that are so much better than what you could get with machine learning. Machine learning algorithms like support vector machines, logistic regression, uh, there's so many models, random forest, gradient boosting. They used what is like a whoever designed those algorithms, you need to feed in handcrafted features to those models typically. So, so what that means is you might want to say that, okay, I want to feed in the NDVI, I want to feed in, the analyst decides what to feed into the model, and the machine figures out how to get the results. So machine isn't doing much. It's the human intelligence and what input to feed into the model that's working. With deep learning, uh, you can typically throw a lot of that data, and the initial layers of the deep neural network can extract the important features from that data. And the final layers or the later layers can work on those extracted features. So that's one difference between traditional machine learning and deep learning. Now, coming in the context of remote sensing, typically these machine learning models like random forests, the maximum likelihood, they you typically worked with one image and you provided data on that image, like samples in that image, and the machine learned from that, and you applied and got the results there. But deep learning is these models, they have many layers of artificial neural networks. They have a larger capacity to learn. They can learn complex patterns, and they can train on huge volumes of data. Once you do that, the model, the trained model can work across a number of images. So our building footprint model works with drone imagery, it works with satellite imagery from different sensors. So it's about the generalizability, the capacity to learn, the learning capacity, and what you feed into the model, I'd say. I hope I answered that well for you.
Hi, Rohit.
Hello, Aligar.
Hello. Yeah. I'd like to make a question. First, thanks for your pleasure presentation. Not really an expert in this area, but I'm interested in applications. For example, road extraction, precision farm, and the other applications. But I would like to present a question about the data you normally is data are normally used in this application, like point cloud from LiDAR, from photogrammetry, using for example dense matching, images, text, time series, and the others interesting data set. But I would like to, I miss the GNS trajectories. How can you use the GNS trajectory, for example, from GPS to present evidence of obstruction, for example, by building, by trees? It is possible to use to supply evidence, for example, obstruction over the road, for example, in urban areas.
Yes. So if I understood the question correctly, well, I'm not really a remote sensing person, but what you're looking for is that if you've got GPS tracks of vehicles, some trajectories, right? And from that, you want to be able to derive what the road could be like, where the obstructions are. So is my understanding correct there?
Yes, yes.
Okay.
Although in
Okay.
urban area, you know that GPS has a problem with the
Yes.
outliers
Yes.
accuracy due to multipath of the
Yes.
GPS signal. You have, I know that this data is complicating urban area, but my question is if the GNSS trajectory can be useful for predict obstruction, for example.
Yes. So one of my colleagues, actually, Mansoor Raad, he has done this exact work, and he used GPS tracks to come up with road networks. And this was, there's noise in GPS tracks because of reflection and uh, from buildings, right? So, but the noise is clustered in using a typical pattern, so like a bell curve, for example. So he used a technique where he was using a classical machine learning approach to find these tracks, the most probable track for the vehicle given a number of GPS breadcrumbs. I'm not sure if I remember that algorithm. I think it was called SOM. I'm not remembering it right away, but you should look and on Mansoor Raad's blog on that. So maybe later when this video is posted, I'll post a comment to more information about this, what exactly he had used.
Okay, thank you.
Mhm.
Okay, so some questions are coming in from YouTube. This is the first one. Can we have access to examples and codes? I think you already answered that with a final slide of yours, pointing out the addresses in GitHub. Are they? That's
Yes.
that, isn't
So
it?
all of the samples that I showed you, they are either already published examples in ArcGIS API for Python, or we've blogged about it on the medium.com/GeoAI, or they are upcoming samples and guides. So even for the upcoming samples and guides, you can go to our GitHub repository, github.com/esri/arcgis Python API with hyphens, and you can look at the current pull requests and get it hot off the oven right away.
Okay. So the next question is from Rodrigo. So faced with so many machine learning applications and algorithms, what should the researcher keep in mind before testing several of these algorithms? Let me follow up this with something else. Of course, there's a whole range of algorithms you can choose from, and depending on the input data you use, you might prefer some of those instead of others. In the case I was pointing out earlier, if you have lots of vector data in an urban setting and you have a new set of imagery to detect changes, so you have to use vectors as the basis for that change detection. What kinds of algorithms would you prefer to do such tasks?
Yes, it's a very good question. And I'd say that it's a little bit of art along with science. So one is becoming like a trained, a trained data scientist is a little bit like a trained carpenter. They know your tools, your different algorithms, the networks, the strengths and weakness of each network, the kinds of inputs they take, what kind of loss uh, do they use that you want to minimize, and how you can tweak it if needed. And coming to the specific one from you, Claude, of you, like, the building change detection, for example, if you've got vector data and you want to detect where new buildings have come up. So one strategy is that since I know that the change detector works well with rasters, I could go from vector to raster conversion and create those labels where the new buildings have come up. So use GIS tools to do an intersection between the old and the new building footprints, find where the new ones have come up and create masks for those and use it. In fact, the example I showed you, the data for that was prepared using that technique.
Okay, nice. Luciana then has a question on ESRI policy here. Is this the first big investment of ESRI in LP to support event detection and all those features you showed today? What are the plans for the near future for your company?
So, well, I would say that ESRI has been in the industry for so long, like more than 50 years, I believe. And it's nothing new for us. It's like true as it ever was. There have been so many waves of innovation over these years, and ESRI thrives on innovation. ESRI is one of those companies that invests perhaps the largest amount back into R&D. So 30% of our revenue is invested back into R&D, and that's the reason why ESRI is the industry leader. And ESRI is driven by the vision to make the latest technology, the most useful, latest and greatest technology, and use it to solve people's problems, use it to solve industry problems. So it's very user focused. So we look at certainly what's happening in the industry, we look at academia, we look at research, and then we see how to bridge the gap and really solve people's problems. And that's been true over the years, and that's going to happen again in the future. As to what's going to come next, your guess is as good as mine. So as you can see, every month is in this rapidly evolving field. There's a new model that's breaking all records. So our job is, in the R&D center to keep abreast of what's happening, and then by looking at our user problems, trying to bridge the gap between the academic research and the practical usability and putting things into production.
Okay. So there's another question here from John Perez. I think he thanks you very much for the presentation and asks if this project works with any framework, such as TensorFlow, PyTorch. I think you mentioned that. It is intended for a particular one. Do you prefer any kind of platform for ArcGIS code?
Yes. So ArcGIS Learn is actually built on top of what we find the easiest and the most powerful platforms to build upon. So one is our developer productivity. Another is it able to solve people's problems? Is it efficient? And for that reason, we are never tied to an underlying technology. And an example, ArcGIS Learn, if you look at it, it's built on top of PyTorch mainly, but when we go to deploy these models on the field, on the edge devices, it's also built on top of TensorFlow and Keras for that objective. And it uses Hugging Face transformers as our NLP backbone. That's the area, that's the library that's giving the best results these days. It uses fast AI. You can see that learning rate finder. A lot of great ideas are coming from fast AI. It uses Spacey, and we are constantly evolving it. So we are not tied to one. We look at what's best out there, and we use that.
So we have another question from Veihav. I don't know if I say the name very well, but the question is there a deep learning model in ArcGIS Pro to extract features for cities of developing countries? For example, Mumbai, India.
Yes, so yes, you were right. That's WebHub. You got that right. Hello, WebHub. So the question is there a deep learning model in ArcGIS Pro to extract features for cities? So I would say that if I'm understanding your question correctly, you want to identify urban areas, and that is can be thought of as a land cover classification. So there is a model that I shown that does land cover classification based on Landsat scenes, and it's able to identify urban areas. And that's one of the classes there, that it's urban or a developed or a built up area. So you could use techniques like that kind of model to identify where human settlements are. Okay, I see
Yvonne,
a question.
Murilo?
Yeah.
Oh, shit, that's the question. If you could provide some advice for students to how to start with this subject. There's also another one in YouTube asking if you have in India programs and training centers to develop geospatial skills, such as the use of Python libraries for AI.
Yes. So to answer the second question first, like starting with how you can use and learn about deep learning in ArcGIS, we've got many resources. We've got the we've got the guides and the samples that I've shown you. There are also learn lessons on learn.arcgis.com, where there are examples of how you can use deep learning to find where trees are and find their health of trees. And on training.esri.com, there are many talks that you can walk. There's also some courses. Now, if you want to go deeper and you want to learn about deep learning in general, coming to the first question, I would say, like I mentioned, uh, as of now, I think deep learning still needs a little bit of Python. That's like the language of choice, the lingua franca of machine learning and data science in general. So if you've got like about a year of Python experience, I would highly recommend Jeremy Howard's Fast AI course. There have been several iterations of those, and uh, I myself have actually picked up deep learning from there. So it's an incredible resource for you to get started. And it's not as if, he really goes like with a top down approach. So very quickly you can learn how to use deep learning, but then he goes into the depths of it and tells you all the minute details that you need to be able to really be good at deep learning. So I highly recommend Fast AI course for that. Another couple courses, if you want to go, if you are already, with a mathematical background, don't mind those equations, don't mind the linear algebra or calculus, then go to CS231N in Stanford. Those lectures are available online on YouTube. So very good courses for that audience there. And
Yeah,
similarly, the
I think
CS2 to 4. Go ahead.
no, I think your answer is perfect for something I've been telling some students here. I'm from computer science, from databases,
Mhm.
and I think there's lots of opportunities for interdisciplinary work here. Not all of us will be experts in the computer science behind those models or the mathematics behind those models. But those of us who tend to go deeper into that, will have to learn something from the application side of things as well. So I think some of the answers here for the concern of learning these new techniques and things is that computer science will not solve alone those problems. But without computer science, you won't be able to do that. You won't be able to go deep into that without knowing some of the basic uh, computer science and statistics and mathematics behind that. Or you will be only using pre-made models. Those are important too, but in terms of making the field advance, we need people that have the courage to move beyond their borders of their courses or their majors to follow up on those other directions as well. So I think your observations on that are perfect. People can look for training in that and learn more about those things, but they need to be aware that they have to face lots of different subjects and to have to go into areas that are not their original intentions in their graduation, for example. So
Exactly.
thank
So,
you for that answer.
I actually come from an architecture background where, you draw, design buildings and all. So it's about what your passion is, and taking your career in that direction, like some advice for students. And what's great about this generation is that with YouTube, with the internet, today, the best teacher in each narrow area of your focus, the best lectures, they're all available online. You need to know the difficulty is finding what's the best one. But once you found that, just stick with it, and it's incredible how much you can learn.
Yeah, sure. So anyone else? I think Veraldo has dropped out of the connection. So we're on our own here to go on. Any more questions, everyone? Anyone? Oh, Webhaft has another question here. He thanks you for the answer and would love to hear more on extracting building level features for cities of developing nations. I think I can relate to his question in terms that sometimes in Brazilian cities as well, there are regions in which the buildings are so convoluted and so mingled with each other that maybe the techniques used for the United States or for Dubai that you showed are not really
Exactly.
appropriate.
Absolutely. And I totally agree with that. And that's, it's a whole new level of complexity. So like I say, like I'm not going to drive a self-driving car till it can drive in New Delhi, where I am, in the old town, right? It really needs to work there. So on a more serious note, these models, the USA model actually does work well, where the buildings are separated, they're not so congested. So it's about, and that model was trained on data from the US. Now, it's also an issue that where we've got the training data for, that's where the models are going to be developed. So this is known as a measurement bias. Whatever you can measure is what gets amplified. You can create models on what you can measure. But there's also data, from other resources like Street Map, the OSM, and they have data for developing countries. And we are working on creating region-specific models that will do better in different geographical areas. So over time, you can expect to see, with improved data in these locations, more data with the improved algorithms such as the point trend one that I showed you. These models are going to start working in a lot of these other complex scenarios as well.
Okay, thank you. I think we're getting near the time limit for our session. So I'd like to ask all the other participants if they have any other comments for us to finish up. And once again, thank Rohit for all his knowledge he shared with us today. Angela, Luis?
No, I have no
extra
questions,
comment.
but no comments. Thank you for the presentation and for being here with us. Thank you very much.
Thank you so
Thank
much.
you.
I
Okay, I
really
think
enjoyed it.
Thank you very much for our presentation. It's very nice application. Thank you.
Thank you. All right, then, everyone, have a good day, and we'll see you later. Some other talk. Bye-bye.
You too.
Okay,
Bye-bye.
have a nice day, night, evening, afternoon, or early morning, anyone. So because there are people from all over, it's just so surprising, the range of people. And thanks again, Rohit, that was excellent. And I think we'll have the video for this presentation here will serve us as professors to motivate lots of students in the near future. So thanks a lot again. And thanks everybody for the questions, for the participation, and we're calling it a day. Thanks very much.
Thank you.